The fourth application of chain rule we'll cover is called related rates. And here we're going to consider situations which are changing as time is changing, and we're going to use calculus to solve problems. But we're going to see how in applying the calculus, we're going to see how rates show up because of the chain rule. So here we have a standard related rates problem, standard type of related rates problem. A 10-foot ladder is leaning against a wall. Okay? It begins to slip so that the bottom of the ladder is moving at a rate of 3 feet per second. Okay? How fast is the top of the ladder moving when the bottom is 6 feet from the wall? Well, that's a lot of information. The first thing I always like to do is draw a picture. Some of these you won't necessarily need a picture because it's just like a sphere. But here we have a lot of things going on, so let's draw a picture. 1. Draw a picture. And what do we have? We have a 10-foot ladder leaning against the wall. So here's the wall, here's the ground, here's the 10-foot ladder which is leaning against a wall. Well, in drawing the picture, we're going to want to label our variable. So in this situation, something is happening as time goes on, which causes some of these quantities to change as time goes on, which means some of these quantities are variable. Which quantities change? Well, it's always a 10-foot ladder. So this ladder leaning against the wall, I don't have a short enough stick. Maybe this candle will show up. The flag might be too big. So we have this 10-foot ladder leaning against the wall. What happens as time goes on? Well, it begins to slip, which causes a couple quantities to change. The 10 never changes, but the other quantities do. Which quantities? Well, let's call this one x, and let's call this one y. So as this ladder slips, x is getting smaller, y is getting larger. But in particular, x and y are changing. So the first thing I like to do is always draw a picture. And I'm just going to further emphasize the point. Notice x and y change as time changes. What does that actually mean in math? Well, it means x and y are functions of time. So, parenthetical, x and y are functions of time. So x and y are functions of time. Quantities which change as time changes are functions of time. The next thing I like to do, well, usually the next thing I like to do is retranslate the question in terms of this picture using calculus language. I stepped on the microphone. 10-foot ladder. I don't know if that makes a loud noise when I step on the microphone. I think it might. 10-foot ladder leaning against the wall begins to slip so that the bottom is moving at 3 feet per second. Well, that's going to be relevant in a moment, but what is this question actually asking? How fast is the top moving when the bottom is 6 feet from the wall? Well, how fast is the top moving? Well, how fast it's moving is given by a rate. What measures where the top is? X measures where the top is. So, number 2, I like to translate the question into calculus. Translate the question. So what do we want? How fast is the top of the ladder moving? Find how x is changing as time is changing. X measures the top, time measures time. So how fast is the top moving with respect to time? How is the top changing as time is changing? Remember, the derivative tells us rates of change, and in this case, x is a function of time, so the derivative is going to tell us how x is changing as time is changing at a given instant. This question wants dx dt. When does it want dx dt? Well, it wants it when the bottom is 6 feet from the wall. what measures where the bottom is? Y. It wants dx dt when y equals 6. I did intentionally write this lower because I'm going to put something else there. But what other information is in here? 3 feet per second. What's 3 feet per second? The bottom is moving at 3 feet per second. Y is changing at 3 feet per second. So dy dt is 3 feet per second. So this question is really saying find dx dt given that picture when y equals 6 and dy dt is 3. Well, there's a little more information we could take just from this. If y equals 6, then x equals 8, because it's a 3, 4, 5 triangle. So this question is really saying find dx dt when y equals 6, dy dt is 3, and in that situation, x equals 8. Once we've translated the question, that will make a future step much easier, because all you have to do is look at those numbers. But before that, we do need an equation relating x and y. Well, what equation do we have? So I'll just say equation. What do we have? We have x squared, Pythagorean Theorem, x squared plus y squared equals 100. Well, now we have our equation. X and y are functions of time. We have all these numbers up here, so we can now solve this. So I'll say differentiate for 4. Differentiate with respect to time and solve. Differentiate with respect to time. Well, remember, x and y are functions of time. So if you differentiate with respect to time, you can think of this as being a large quantity with t's squared. How do you do the derivative? You use the power rule and the chain rule. So you get 2x to the 1. Remember, x is full of t's. 2x to the 1 times the derivative of the inside. The derivative of x here with respect to time is dx dt. Remember, x and y both change as time is changing. So 2x from the power rule, dx dt by the chain rule. Similarly, y is a function of time, so we get 2y to the first times derivative of the inside times dy dt. Derivative of y with respect to t is dy dt equals, how is 100 changing as time is changing? Well, 100 doesn't change as time is changing. 100 is 100. Well, now we have this equation, and again, power rule to get the 2x, and then chain rule to get dx dt, because x is a function of time, and we're differentiating with respect to time. Well, and similarly for y. Well, now we look back to our translated question. We want dx dt. Well, look at that. There's dx dt. But it's not alone. We want dx dt when x is 8, y is 6, dy dt is 3. Well, so you could solve for dx dt and then substitute, or you could substitute and then solve. I guess this time I'll substitute and then solve. Yeah, okay. So we have 2 times x. You can cancel 2's if you want. 2 times x is 8, dx dt, plus 2 times y, 2 times 6, dy dt is 3, equals 0. What do we get? So we get what? 16. I really should cancel the 2's. So you get 8 dx dt equals what? Negative 18? Because we canceled the 2's, divide by 8. So dx dt is negative 9/4 units feet per second. So here, standard related rates problem. For all of them, I do like to retranslate the question with our given variables, because the question is not going to say use these variables. But keeping track of the variables which change as time changes is very important in related rates, or for related rates. Now, this question, the answer was negative. Does that make sense? Well, I'm erasing it. So you might think, yes, it does make sense, because I wouldn't erase it otherwise. I also put a square around the answer. A square with sides that aren't the same size. So does that answer make sense? Well, I'm going to write the next question, and while I'm writing the next question and leaving the relevant information, you can determine if that makes sense, or decide if that makes sense. So we had one here with triangles. Example, a spherical balloon. Maybe I shouldn't talk if you're trying to figure that out. So in that previous example, the negative answer is correct. Why does that make sense? Well, what's happening as time changes? This ladder is sliding down. X is getting smaller. So it does make sense. And in the question it said the bottom is moving at 3 feet per second. That also makes sense because Y was getting larger. So next, a spherical balloon is being filled. Oh, I wrote inflated in my notes. Well, whatever. Is being inflated at 3 cubic feet per second. How fast is the radius of the balloon changing when the diameter of the balloon is 14 inches? So notice these related rates questions. These first two said, what is happening at a given instant? And remember, the derivative allows us to figure out what happens at a given instant. So we have the situation that's changing. What happens at an instant? Well, what do we have? A spherical balloon. Well, we're being asked about what? How fast is the radius of the balloon? So, I mean, you could draw a picture. It's a sphere, if you want. But I'm going to go straight to translating the question. Translate the question. What does this question want? It wants how fast is the radius of the balloon changing. I'm going to use R for radius. Find dr dt when the diameter is 14. We're not going to use diameter. Radius is 7. But also, it's being inflated at 3 cubic feet per second. So the volume is changing at a rate of 3 cubic feet per second. So we have, find the radius, find the change in the radius when the radius is 7 and the volume is changing. Well, now we need an equation. Here, our equation is going to relate volume and radius. The volume of a sphere is 4/3 pi r cubed. Any volume or area formula that could show up, you'll see. It's not gonna, if I put one you haven't seen on a test or something, I'll give you the formula. There was one, I think it was a final one year. We didn't talk about cones at all in the semester, but on the final I asked about cones, so I gave the formula for volume of a cone. But if we have seen it, I won't give it to you. So here we have our equation relating volume and radius. Now we just need to differentiate with respect to time and solve. Differentiate the left with respect to, I'm going to do this over here. Differentiate the left with respect to time. Well, remember, volume and radius are both changing as time is changing. Derivative of volume is 1. Derivative of v is 1 with respect to time. But you need 1, and then you need to apply the chain rule. So it's 1 times the derivative of the inside. 1 times dv dt. On the right, 4/3 and pi are constant. Derivative of r cubed is 3r squared. But we're differentiating with respect to time. R is a function of time, so again, a rate is going to show up by chain rule. And now we just need to substitute and solve. Here's dr dt. So I'll solve it like this time. So dr dt is what? It's 1 over 4 pi r squared dv dt. So just divide by the thing in front of dr dt. Substitute. What do we get? We get 1 over 4 pi times 49 times 3. 49 and 3 make 200 without 4. Also known as 196. And our units are feet per second. Because it's asking about the radius, which is in feet, but it's a rate, so it's feet per second. So you could be asked one with shapes like that. Let's look at a couple more. So the ones we've done so far have used 2 variables. Let's look at one where we're going to have a 3rd variable. At noon, ship A is 100 miles west of ship B. Great. Ship A, at noon still, ship A sails south at 25 miles per hour. And ship B sails north at 35 miles per hour. Find the rate at which the distance between them is changing, well, is increasing, I wrote. Is increasing at 4 p.m. So again, we have a situation which is changing as time is changing, and we're going to use calculus to figure out what happens at an instant. Well, we're going to see where a 3rd variable shows up. So let's draw our picture. I might need a blue marker too for this. I don't know, let's see. At noon, ship A is 100 miles west of ship B. So right here, we have ship A is over here, ship B is over here. I always like X and Y, so maybe I should have even called them X and Y. This is like the 8th time I've done this example, and this is the first time I thought of naming them ship X and ship Y. But whatever. They're 100 miles separated. So this distance right here is 100. Why is he putting it so off-center? That distance is 100. Ship A sails south at 25 miles per hour. Ship B sails north at 35 miles per hour. So right here we have some quantities which are changing as time is changing. This distance here is changing as time is changing. Call it x. This distance here is changing as time is changing. Call it y. Ship B is here, ship A is there. So we have those quantities which are changing as time is changing. Is that how I labeled them here? Yes. Find the rate at which the distance between them is increasing at 4 p.m. Well, I don't see the distance between them anywhere here. So we'll need to draw the distance between them. So the ship is up here, the ship is down here. Right here, we have the distance between them. This ship is going to keep sailing south after 4. That's going to keep sailing north after 4. But we're looking at the distance between them. That is another quantity which is changing as time is changing. Call it z. I don't draw my z's diagonally unless it's labeling something diagonally. I do draw my z's like that. I always put a line in the z's because, if I don't put a line in the z, it looks like a 2. And I never liked drawing 2's like that. Well, actually, I did like drawing 2's like that for about 10 years. But I realized that I didn't like it, actually. So we have this situation. Great, let's translate the question. Find the rate at which the distance between them. Well, what measures the distance between them? Z. So, question is asking. Find dz dt. Notice we're being asked about the distance between them. We're not using any distance formula. The distance formula is a way that high schools make the Pythagorean Theorem unclear. You'll notice up there there's a ladybug. This house is pretty old and it is susceptible to ladybugs. So if you see anything flying around, it's probably a ladybug. Find dz dt. When do we want dz dt? Well, we want it when what? We want it at 4 p.m. What are x, y, and z at 4 p.m.? Well, our variables are x, y, and z. So we're going to want a when x equals, a when y equals, and a when z equals. What happens at 4 p.m.? Well, ship A sails south at 25 miles per hour at noon. 4 p.m. is 4 hours later. So 25 miles per hour, 4 hours, give us 100. Ship B sails north 35 miles per hour. 35 miles per hour, 4 hours, 140. Z is 260. Why is Z 260? Well, I'll explain why Z is 260 in a moment, but for completeness, you can just throw 260 there now. And no, I did not do that in my head. As I mentioned before, I've done this example a bunch of times, so I know Z is 260. Where were we? Find dz dt when that, but we also have other information, and we have rate information. Ship A sails south at 25, so dx dt is 25 miles per hour, and dy dt is 35 miles per hour. So find dz dt when all of this happens. Now, why is z 260? Well, we'll see that once we get to our equation. What's our equation? Oh, I probably should have told you to leave a gap here, leave something here. I didn't. Well, that's okay. Equation. I don't see an obvious relation between x, y, and z. You can try to break this down, but where this z line intersects this 100 changes as time is changing. So that's going to introduce a fourth variable if you try to use this divided into two triangles and so on. But what we can do is draw extra lines. We can draw those lines. This now is a rectangle. This side is x. This side is 100. So now, with this big right triangle, we do have a relation between x, y, and z. What is it? Pythagorean Theorem. 100 squared plus this side squared equals z squared. Now we can differentiate and solve and so on, but before we do that, now we can figure out why z is 260. Well, why is z 260? Well, if x and y are 100 and 140, I'll draw it here, but then I'll erase it. So z is 260, so you may want to block this off. Z equals 260 because of the big triangle with sides 100. What's the tall side? 100 plus 140? 240. So in the first example, we had a 3, 4, 5 triangle. Here, we have a 5, 12, 13 triangle. 5 times 20, 12 times 20, 13 times 20 is 260. So now we're going to differentiate and solve. This differentiation is, I would consider, more complicated than previous ones. So you could square everything out. If you do that, a product rule shows up, and I think that's a little inconvenient. Well, more inconvenient than what we'll do. So differentiate 100 squared doesn't change as time is changing. Differentiate with respect to time, we have something squared. So the derivative is 2 of them to the first power, but then you need to multiply by the derivative of the inside using chain rule. We're differentiating with respect to time. Derivative of x with respect to time is 1 dx dt, plus derivative of y with respect to time is 1 dy dt. So that's what we get on the left side. 0 plus a power rule here, 2 of these to the first, times the derivative of the inside, 1 dx dt plus 1 dy dt. If you wanted to use power rule on 100 squared, you certainly could. You get 2 times 100 to the first, but then chain rule multiplied by 0, because 100 doesn't change as time is changing. Or you could just say it's a constant derivative of 0. That's what we got on the left side. What do we got on the right side? Well, again, z, here x, y, and z are all functions of time. So differentiate z with respect to time, or z squared with respect to time. You get 2z to the first times derivative of z with respect to t by chain rule. And now we can substitute and solve. I'll do that like this. So what do we want? dz dt? dz dt equals, what does it equal? Well, divide by 2z. Notice the z's, or notice the 2's will cancel. So you get x plus y over z times dx dt plus dy dt. So divide by 2z, you get that. And then you can substitute. I kind of like how that equation looks, so I solve for it. What do we get? We get 100 plus 140 over 260 times 25 plus 35. And what does this equal? Well, it equals 24 26ths, so 12 13ths times 60. 6 and 12 makes 72. And 13 does not cancel with 60 or with 12. So we get 720 over 13 miles per hour. That's how that's changing. So I would consider this one significantly more complicated than the first two because of the third variable, but also because the differentiation was a little, I mean, it's the same as far as chain rule is concerned, but it's a little different in the details here. this board is, I'm going to have to put another piece of fun noodle under that so it pushes it up. Let's look at one more example. The volume of a cube is increasing at a rate of 10 cubic inches per minute. Period. How fast is the surface area changing, increasing, I wrote. So in the previous two examples, our rates were positive. The quantities were increasing as time was changing. How fast is the surface area increasing when the length of an edge is 3 inches? Some may consider this one easier than the previous one. Some may consider this one harder than the previous one. I personally consider it harder, because it requires two separate observations, whereas the first couple examples we did really required one observation. You know, the second one did have a fair amount of details, but it really did boil down to a triangle with a chain rule computation on that. But here, we have to be very careful with our organization. The volume of a cube is increasing 3 feet or whatever, 10 inches, and so on. With all of these, I'm not going to do anything stupid with units. The units will all be, I'm not testing you on your ability to convert units. That's, well, it's actually something we're covering in my Math 101 class. But that's not important in calculus. The units will be fine. The volume of a cube is increasing at 10 whatever. How fast is the surface? Let's go straight to the question. Translating the question. What is this question asking? How fast is the surface area increasing? Find, I'll call surface area capital S. Those of you who take Calc 3 will also use capital S. How fast is the surface area increasing when the length of the edge, which I'm going to call x, length of an edge I'm going to call x. So when x equals 3 and what? dv, the volume is changing. Not 3, that's 10. Inches cubed per minute. Okay, find ds dt. Well, let's get a surface area equation. What's the surface area of a cube? Well, a cube has 6 sides. 6 sides, each has area x squared. So the surface area of a cube is 6 times x squared. 6 I should say 6 faces. Each has area x squared, so 6x squared. Well, find ds dt. Differentiate with respect to time. The left side we get 1 ds dt. The right side we get 12x dx dt. 12x, 6 times 2x. X and surface area are changing as time is changing. So you need a chain rule here. You need a chain rule here. Well, substitute and solve. X equals 3. dx dt. dx dt. What's dx dt? That's a v. V and x are not the same in this question. We need dx dt. Question mark. How can we find dx dt? Well, we notice we actually didn't use all of the information we needed. So maybe we can use volume information to figure out dx dt. So let's say to find dx dt, consider the volume of a cube. The volume of a cube is x cubed. Differentiate with respect to time. dv dt on the left, 1 times, with chain rule, dv dt, equals what? 3x squared. Then use chain rule, so 3x squared. X is changing as time is changing. 3x squared dx dt. And now we can solve for dx dt. It's convenient that these wound up on the same board. We can solve for dx dt. dv dt is 10. X equals 3. So 3 times 3 squared, 3 times 9, dx dt. So dx dt is 10/27. What is it? Feet, inches per minute. So to figure out dx dt, we had to appeal to another equation. dx dt is 10/27. So our question mark, 12 times 3 times 10/27. What does that equal? Well, 3 and 27 make 9, 3 and 13, or 3 and 12 make a 4. It's too many numbers, I lost myself. 40 over 9, 40 over 3. 40 over 3, and what are our units? Surface area. Inches squared per minute. So why is it 40? Well, the 10 stays. 12 and 3, but have 2 3s, which cancel with 2 of those 3 3s. You're left with 1 3 down here, a 4 up there, and 10 up there, so 40/3. For these related rates questions, I do not find any of them all that easy. When I took calculus, I actually considered related rates the most difficult part. But because of that, I like breaking them down into, if necessary, draw a picture, and then translate the questions. You don't even have to look at this again. All you have to do is look at the calculus. But then always keep the chain rule in the back of your mind. These quantities change as time is changing. And I will, so these related rates questions weren't easy, but they actually could get much harder. So I will post 1 or 2 other types for you to look at. Maybe we'll discuss them in the workshop if there's some time. But I'll just post some, maybe 1 or 2 extra questions with some solutions. And maybe I'll write something about them and walk you through some of it, I guess, because some of these I have written are pretty difficult. This one I'm definitely going to put up there because it shows some similar triangles. That's nice. But try practicing these. The first thing you should do, I think, is draw a picture and label the variables. It's very important to keep careful track of the variables in these.